one thing I'm going to be doing while I'm mentoring you guys is asking you questions like that, okay? It's not that I don't know the answer. Sometimes it is because I don't know the answer and I'm asking you, question. A lot of the times I'll ask you questions to find out what it is you do know and what it is you don't know, so that I can help you learn the things you don't know. But if, when I ask you a question and I get no answer at all, I don't know where to go from there, okay? So, what is it that our robot needs to do? Anyway.
It needs to shoot.
Needs to,
basketball.
Well,
I mean, shoot. I mean, oh my gosh.
Shoot something, right?
Shoot a frisbee.
but at a higher level than that,
a flattened basketball.
It needs to play this game, right? And how do we know what that game is?
There's a video.
There's a video.
And
what else?
There's this online site which has all the instructions.
Mm-hmm. There are all the competition manuals that explain what the game is and how to play it. Okay? So we need to look at that and decide, right, like Evan said, it needs to shoot, but does it? Does every robot need to do everything? Right? No. So what are the things involved with the gameplay? Shooting frisbees, what else?
Climbing the pyramid.
Climbing the pyramid. What? Okay, carrying frisbees with you. Okay, what else? Moving, right. You got to move from place to place, move around the arena, right? And possibly even pick things up off the floor. So, what are the things that? Before designing anything, you also need to know what your constraints are, right? The most important constraint we have is time. When do we have to finish this robot? Yeah, what's that actual date?
February 19th.
February 19th, right? So by Feb 19th, right, this robot goes in the bag. And you don't get to touch it again until March, okay? So that's, time is our most precious commodity because you cannot make more time, right? You can always earn more money, you can always get more parts, but you can't make more time. So every hour that you guys aren't in here working on this thing is just time lost, okay? What other constraint are there? Money. How much can this thing cost? What's the maximum you guys can spend on building this robot?
What is it? 4,000 or something?
4,000
It's usually around the ballpark of 4,000.
So, $4,000. So that's something you need to keep track of as you're building or as you're designing, right? We're not going to make all the parts out of diamonds and titanium because that would be way too expensive. Okay. I'm getting a lot of blank stares from you guys, which means you haven't read the competition manuals, which tell you all these things. Okay. So what does that mean? It means you guys need to take the time. Okay. Play a few less video games and read the competition manual. Okay, so size constraints, right? So in the rules there are size constraints. There are a whole bunch of. It's less than 100, but there are a lot of rules that the robot has to comply with. Okay? So before starting to design it, you guys need to understand what those all mean, because those will restrict what it is you do, materials you use, power sources, right? All kinds. So, all right. As far as gameplay, I think we've already made some choices on what we're going to do. Right? We are going to what? Shoot. So we're gonna shoot frisbees. What else?
I don't know if I would.
Okay.
Yeah, I think
So we're gonna make an attempt to design and build something to climb. Okay. Certainly we're gonna move around, right? And are we picking frisbees off the floor or not?
No.
Okay. So if we don't do that, what do we need to do?
We hand it to them.
Right. So you need some sort of system that will take discs from the feeder stations, right? Okay. Okay. So I think we should go over the what it is that makes up all these different things, all the things that components that we're going to build these out of, and because I think we've been exposed to it yet. We have completed versions of robots in the lab that you guys can take a look at and ask some questions about it. All right, once we go over this. Okay. So the main mechanical portion of the robot is going to be some sort of a frame, right? That's what's going to hold this whole thing together. And according to the rule, there's size constraints.
Well, you met him,
So part of our constraints are going to be size, right? Weight. How much can this thing weigh? 120 pounds. Right? So weight has to be less than 120. And size constraints, there's actually several different, right? There's height, width, length.
It's just perimeter seriously.
The perimeter height is like 84
Well,
inches.
there's height, but there's no length and width. It's just perimeter.
There's,
54-inch
yeah, I think
diameter.
there's a, yeah, there's a.
Yeah, because you had to
Cylinder.
fit in a 54-inch cylinder, right? So then that one is what your maximum was. Okay, so just a basic robot, we're gonna have a frame that's gonna hold everything, right? We have a couple of wheels, maybe 4, maybe 6, maybe 2. So you guys can decide. The way that we're gonna get this to move is to put right? You're going to put an electric motor in it, right? And the way electric motor works is you put electricity into it, and it has a shaft that comes out of it, and that spins, right? So we're going to use this motor to turn these wheels through, sprockets or something onto the wheels. And have a chain or something that goes to another sprocket on the motor. So putting electricity on the motor is going to spin the wheels will turn, the robot will move. Okay. We need to figure out what gear ratio we're going to use here, and I'll work with the mechanical guys later on to figure out what exactly it's going to be. All right. That depends on how much this whole thing weighs, the configuration, how far apart your wheels are, size of the wheels, which motors you're going to use. Okay. All right. Right. So let's go back to power source. There are only 4 different sources of power that you can have on your robot. You guys know what those are?
Oh, types of motors.
No, power source. Where the power to do any movement comes from.
The battery?
Battery, right? So the main one is that 12-volt rechargeable battery. Well, indirectly, right? Compressor is a motor connected to an air pump. That's powered by the battery. So actually, it's just a transformation of the power type. Right? You take electrical power, run it to the motor, the compressor turns that into compressed air. And then with that compressed air, you can use it. Okay? But you can also start with just an air tank that has air pressure in it. Right? So that's another source of power. Okay? You can also have,
No, just kidding, probably
what?
not. I said solar, just kidding, probably not.
no.
No.
Because solar cells will break, it'll get glass all over the field.
Not that there's much sun in there, you know. Anyway.
And third source is deformation of parts,
Springs?
springs, right? So you can have elastics, springs, torsion bars, right? You can take a piece of a rod of metal and bend it, kind of like a crossbow or a bow or two arrows. And the last power source you're allowed is the change in the center of gravity of the robot, which means you can have a giant weight held up high that has a certain amount of potential energy. And as you allow that to fall, right, it releases energy. You can, the potential energy becomes kinetic energy, and you can use that to power things. Right? That's how certain types of catapults work. Giant weight up here. And as that falls down, that energy gets transferred into the thing that you're shooting. It shoots. Okay, so right. So any shooters or climbers, right? Those are going to move because we're going to use either electric motors, pneumatics, release a giant spring of some sort, which is one of the most dangerous things we can do. So if we do anything with elastics or springs, please consult me heavily, because that can be very dangerous, because it oftentimes doesn't look like anything's going to happen. So it can release a lot of energy very quickly. Okay, that's okay with that. So, the shooter mechanisms, the climbing mechanisms, are all going to have some sort of structure, that main structure that holds it together, and then it's going to have mechanical, actually moving mechanisms, right? Because what you're going to do is take energy from one of your 4 power sources and do something with it. You're either going to take some of that energy and put it into the frisbee, which then causes it to shoot away from you at a certain speed and in a certain direction. Or you can take that energy and use it to raise the robot off the floor, right, as you climb the pyramid. Or use that energy to propel the robot across the arena. Okay? So I think the most mysterious thing is how do we get all this to actually work? How is it we actually control these motors? So let's see. How many of you guys have actually built anything before? Even, or in here, in the class, in the club, built anything, right? Use tools to cut materials and use other tools to attach those 2 pieces of whatever to do something else or to each other. Okay. We're going to have to do a lot of that to build our frame structure, the mechanical structures. All right, so let's just talk about the electrical. Okay, so we have our power source, right? Battery. What does that battery connect to? The battery has a plus and a minus. Well, you guys all know how electricity works?
It's like water.
Kind of, yes. It can be, well, at times you use the water analogy. to understand it. We say that electricity on a power source, like a battery, is trying to flow from the positive terminal back to the negative. In actuality, what's happening are electrons are going from negative to positive, but that doesn't matter. We always, you can look at electrical flow either direction, but most people like to think of it as flowing from positive to negative, as if it were water flowing. But like water, it needs something to flow in. So we use wires, which have very low resistance, so that electricity easily flows through them. Everything that's surrounding it, like the plastic insulation or the air around you or your body itself, has higher resistance, so the electricity doesn't flow through those things. So in order to use the energy that's in this battery, we're going to have to somehow get it to our motor, right? So our motor lead will have a plus lead and a minus lead, right? Red wire, black wire. And somehow we have to get this energy to this motor in a controlled way. The way we do that is we use these electronic speed controllers, okay? And these are just basically a giant switch that switches very quickly. So, right, these will have a plus and a minus terminal, and then for the motor side, it'll have what they call a plus and a minus terminal. So this connects directly to the motor. This connects through the on-off switch and power distribution panel. So coming out of here, we want to have a way of turning this power on and off. And so we'll put a switch here. That's the schematic symbol for a switch. Okay? The negative end we can connect directly to this electronic speed controller. That's not exactly true. Okay. Okay, so this is our main breaker, which you all should know how to operate. Then this goes to what we call the power distribution box. Okay? So that has a plus and a minus connection. What this is really just a fuse panel. We'll have a bunch of different breakers in there. So internally, the plus is connected to each one of these breakers. Okay? And they'll all be rated for something like 40 amps or 30 amps. Okay? These are resettable circuit breakers. What happens is if the current exceeds this amount, this rating, this will actually open up and then stop the flow of electricity. Okay? Until this cools back down, and it makes the connection again. Get that? So say externally here, you accidentally wired this to here. There's this extremely low resistance path back to the battery, and this current can be, over 100 amps. Okay? It can, as this high amount of current flows through here, it will heat this wire up. If it didn't have the circuit breaker, this wire will probably eventually heat up so hot that the insulation will catch on fire. Okay? If you were to touch this wire, it would just burn right through your skin into your flesh. It'd be very, very painful. Okay? And can cause a fire. So, to prevent all that, we put circuit breakers in there. Okay. So, on the board, you'll see a bunch of red and black connections. Each one of the red connections goes to a circuit breaker. Each of the black connections actually gets connected to this negative terminal up here. So, if they were to take two of these, right, one leg of this, and go to a speed controller. That then goes to a motor, which which acts like a switch. So, if it's full on, this motor will be running at full speed. there's actually a little computer in here running a little bit of software that can switch this at about 2,000 times a second on and off very, very quickly. And so based on the amount of time that it's on, each time it turns on, you can actually vary the speed of this motor. So we're going to have a lot of these. We're going to have at least 2 of these for the drivetrain. We have at least 1 for the shooter, however many you guys decide you need for clanging. Okay. Then, the way this is told what to do is we have our C-RIO, which is going to be the brains of the robot. Okay? So this is another little computer, and we're going to write the software for this computer to tell it what to do. Okay? So one of the things it does is control the speed controllers. So there's a control signal called PWM, which this generates. It's an electrical signal. It goes to this speed controller and tells it how fast or in which direction the motor needs to turn.
Sidecar?
What's that?
The sidecar.
Yeah, it actually comes from the digital sidecar of the C-RIO, but just for simplicity, the electrical guys. Okay, so right. So like any computer, C-RIO isn't useful unless it has inputs and outputs. So what are some of the, right, one of the outputs is driving the PWM signal out of the vehicle sidecar, going to the speed controller. Another one would be solenoid signal from right. There's a special card that goes in the C-RIO that drives what they call a solenoid bumper, which is just a breakout board or a board for connecting to solenoids, which are little electromagnets that control airflow. Okay. So if we have air pressure going into the solenoid valve, the C-RIO software can turn this on and off, and then we can use this air pressure to move pneumatic cylinders. Okay. Those are the main inputs. We can use these to turn lights on and off. There's also spike relays, which are electrical switches. Right? So you can, if you had a spike relay hooked up to a motor, the only thing you could do is tell it to be off, so that it doesn't rotate at all. Rotate full speed in one direction, or rotate full speed in the opposite direction. If you need a speed in between full speed, you'll have to use an electronic speed controller. Let's see. So, what are okay? So some of the inputs to the C-RIO can come from sensors on the robot. You can have photo sensors. There are position encoders that you could put on the end of the motor shaft, so you could actually tell how fast it was spinning, or if it was spinning at all. No? Okay. Need some help? A very important one is is limit switches. Okay? So say you're using this motor to move an arm, but you need a way of knowing when to stop that. You can have a switch that gets pressed when the arm is reached as far as you want it to go. The C-rail will know that, oh, that switch is pressed, stop, telling this speed controller to move this motor, and then the motor will stop, and the arm will stop. Okay, take it. Watch this. Now, a very important input and output on this is actually an Ethernet connection. Okay, this is how we're going to communicate to the C-rail. Right? All this stuff is in the robot. This is our wireless bridge or access point, depending on how we have it hooked up. So, now, going back down to the driver station. The driver station has size constraints. Does anybody know what those are? Does anybody know where to find them?
It's online.
Okay. There's a size constraint, right? Why?
You only get like a certain amount of space when you go to the field.
Right. So on the field, there's at each Alliance wall, there's a shelf that your driver station must fit on. Okay. So in order to build our driver station, we need to know its size constraint. Is there any weight constraint?
I think so.
No. Okay. But the size constraint just tells us the maximum size it can be, right? We may have other reasons we want it to be smaller, right? So that it's easier to carry around, right? So it is something you're going to have to carry onto the field and off the field. So it'd be nice if it had handles. It was only as big as it needed to be. Okay. So the driver station is going to have some sort of mechanical structure to hold all the pieces that it's comprised of together, and so that we can just move it to the driver station or the Alliance wall shelf as one piece. We just put it down, plug in the wires we need to into it, so that can be done very quickly and be ready to play. Okay. This is actually, the heart of it is actually a PC, right? It's the little classmate computer, okay? Connected through a USB hub, we're going to have input and output devices, okay? This is going to have an Ethernet connection right now to a router, but then later on at the competition, this Ethernet connection actually goes to what they call the field management system, so that they're able to control our wireless connection to the robot and actually cut you off if they need to. So through the field management system, they can tell whether you're actually communicating with your robot, right? So they won't start the game until they know everybody's got a connection between their driver station PC and the C-Rio in the robot. And then during the game, if they need to disable your robot, they'll cut off this wireless connection. Okay. For safety. So, in this PC, you have a piece of software called the Driver Station. What's its official name?
Driver station, I think?
Driver Station.
I think it is called Driver
There's a
Station.
program, yeah, that's in there called Driver Station. And what it does is it communicates through the USB port to any input devices you have. figures out what it is you want to tell. It reports, right, the position of all these input devices to the robot through the Ethernet port. So it will take that data, form it into packets, send that packets via Ethernet to the router. The router sends it wirelessly, right, through Wi-Fi to here. Okay? And then the serial, this packet will be right by the bridge, be translated from Wi-Fi back to Ethernet, wired, right, protocol, into the serial. The software in the serial will see this packet, say, oh, this is for me, and read the information out of it, and then the software that you wrote that's running in the serial will know what that means. Oh, this joystick, right, joystick 1's x-axis moved is at this position. That means I need to tell this speed controller to be at this speed. Okay. This connection is actually bidirectional. So you can have sensors on here, like a temperature sensor. At the minimum, you need to have a voltage sensor that this reads, that reports that value back to here. And on the screen of the classmate is that's a separate program, right? Called the dashboard, I think. It's not part of the driver station. They all come up at the same time, I think, but there's another piece of software that will then display. Oh, it is part of the driver station, isn't it?
I think we just call it the dashboard on the driver station.
Okay. All
I
right.
don't remember its official.
Well, whether it's the same application or a separate application, the applications know where to get that data. So you could have things like an encoder that tells you the position of something. You could have, know how fast your robot is going. You could have a temperature sensor on each motor to know whether you've got a motor overheating or not. And do something based on that or not. Another thing you can actually have on here is a video camera. Okay, that video camera actually connects via Ethernet to the serial. The serial can do things based on the video it's seeing. You can actually have software running in here that will analyze the video feed and make decisions based on what what the camera is looking at, like the vision targets around all of the goals. Or you could just feed that video data back through Ethernet and then Wi-Fi and back to the driver station and display on this PC what this camera on the robot is looking at. So you could use that to aim it. So instead of having a tight feedback loop where the serial is deciding, oh, the camera's telling me that the target's to the left, I need to move the robot to the left a little bit before I shoot. You could have that information come all the way back to here. The human player looks at that, decides what to do. Oh, I need to move it to the left, moves the joysticks a little to the left. That then goes out to here, tells this motor, speed controllers which way to go, and then the robot moves a little bit, and then you press the button that makes it shoot. Right? In order for the robot to do all that itself, it needs to have a lot more intelligence built into the software, but it can do it a lot quicker if it's because there isn't that delay of someone deciding what to do. Okay, so what kind of input devices can we have on this PC?
Joysticks and that stop button.
Right. At the minimum, you could have a joystick, right? So the e-stop button goes into the USB hub. It's just a big on-off switch. Once you hit that, it tells the driver station software to send a message to the serial to shut down. Okay, to stop everything. stop all motors, stop all solenoids. It's like hitting the disable button in the driver's station software, which will then ignore any input you give to the joysticks or whatever you have over here. When we're on the actual playing field, we won't need that button because there'll be another button up there, big red button, that goes directly to the field management system, which will then disable the robot by disconnecting your wireless connection to your robot through the field management system. Okay, so other than joysticks, what could you have as input devices? You guys all have computers, right? Do you all have joysticks on them? No? What do you have?
Mouse, right?
Huh?
Got a mouse.
You get a mouse, right? So you could have a mouse. You could drive and control this thing with a mouse. What else?
External keyboard.
Yeah. Either the built-in keyboard, because this is a laptop. You could have another keyboard. What else?
Controllers.
Yeah. Video game controllers. You can have an Xbox controller, PlayStation controller, right? Wiimotes. What else?
Touchscreen input.
Yeah, touchscreen. You could somehow connect a tablet to this. It would be a touchscreen. All right, connects. Use one of those. So you wouldn't even have to touch anything. Okay. Using some of these may require special software. Or special hardware out here in order to make one of those act like the device that we already have the driver software for, right? So you could build some hardware over here that connects to just, massive array of switches, and that just acts like the joystick buttons that you have, okay? So that's one thing you need to figure out is what input devices we're going to have, all right? So that goes along with what functionality we have in the robot, right? Because any one of those can tell any one of these devices what to do, but is it the best way to do that, right? Because joysticks, you could use a joystick just to turn a spike relay on and off, but that doesn't make as much sense as using a button, right, which has two positions, either you're pressing it or you're not. This switch is either on or off, right? But you could use a joystick, and software in here can know that, okay, don't flip the switch until I push the joystick all the way to one end or the other, okay? It's kind of weird to do that, but, that is something you can do. So, decide how is it we're going to tell each one of these devices what to do. Okay. So, that's the basic control system. Okay, so for our cart, we don't really have well, yes we do. We have time constraint rate. We absolutely do have to have this by the time we go to Davis, because you will not be allowed to play unless you have a cart for your robot. Okay, it'd be nice to have it before that, so that it'll make it easier to move the robot around here, because we're probably at some point going to take it outside to test it. All right. So what are some of our constraints on our cart?
Has to fit the robot.
All right, it has to fit the robot, has to be able to all of the robot's weight, right? What else?
It's gotta move.
It's got to move, right? So you got to be able to push it around. Okay, so in all likelihood, I'll end up having 4 wheels. 2 of them should be caster wheels, so that this thing is steerable. And 2 of them should be just fixed wheels, pointed straight, kind of like a shopping cart. You all know how a shopping cart works, right? Right? So what goes wrong if we had 4 casters? Which we've done before, so you remember that, Kimmy?
4 casters.
Yeah.
What
Our
the
cart.
design does here though?
Huh?
4 casters and 2 power wheels then.
No. No, not the robot, but the cart,
Oh.
right? So if you're, imagine a shopping cart that had 4 casters instead of 2 fixed wheels, the whole thing could move sideways.
Oh yeah.
So as you're pulling this thing behind you and not looking at it, it could start to move sideways, and then what happens? You're
It
starting to
crashes
mow
into
people
something
down,
else.
okay? Not a good thing. So if we're gonna have 4 wheels, have 2 of them fixed, pointed straight, have 2 of them as casters, and have your handle at the caster end, so it's easier to push it around and move it. Use a solid handle, don't use a piece of rope, okay? Why wouldn't we want to use a piece of rope?
You get stuck.
Right? If you drop it, it can get under the wheels and get caught, and also you can't push a rope, right? So now you can only pull the cart, but say you want it to stop. If you stop, the rope just gets slack and the cart just keeps on rolling right into you, okay? So you have much less control over it. Like I told you, right, there's gonna be 6 robots on, 6 robots off, 24 people on, 24 people off, all these field resets. So there's a lot going on. You need to have control over your thing. This, this thing with the bumpers and the battery is going to possibly weigh over 120 pounds. Okay, so you don't want this thing just rolling around into people, right? Cutting people's ankles and bumping into them, knocking them over. Okay, so you need to have control over it. Another size constraint is, say we built the cart in there, in that little room, put the robot on it, and want to go outside. So what kind of size constraint do we now have?
The doorway.
The doorway, right, and the hallway, okay? So not only do you have to fit through the door, but once you get through the door, you're going to have to turn left or right, right? Be able to go down that hallway and out whichever door we decide to go out, okay? So whoever's designing the cart, right, there's a lot of important stuff that you got to pay attention to. It may sound simple, but if you get some of those wrong, we may not ever move it out of that road. Okay. Field. Who's working on the field? Bryce. So we got one man operation working on our field.
And his dad.
And his dad.
And
Okay.
Leah.
Leo?
Leah.
Oh,
Girl.
Yeah.
Leah Klassen.
Over there.
No, Leah Klassen is supposed to be making the pyramid sometime. Yeah, Sam.
When is that time?
Probably before we have our climbing done, but we'll, yeah, deal with that as the time comes.
No, deal with that now. Right, so why are we building this field equipment?
Practice.
To
Simulate.
practice, right, simulate, and also to help us design this thing, right? Until you can actually visualize and actually try what it is you need to accomplish on the field equipment, it's kind of hard. It gives you a better idea of what you need to accomplish, right? So the sooner we have it, the better. So So I saw Bryce building goals on the weekend. And I guess there's sort of a plan for a pyramid. Which needs to get firmed up because that's going to be one of the trickiest things to do. So, does everybody know what part of the robot they want to work on? Nobody? Alright, let's go one at a time then. Start.
Probably shooting. Yeah. Launching weapons.
Oh, okay. You're going to be working on the mechanical part of
Yeah.
it? Okay. What about software? Are you going to be doing that again?
Not really.
Really?
I could do it later.
Huh?
I could do it later. Maybe
Okay.
after Jerry's gone. 'Cause-
Where's Jerry going?
Well, he's not going to be here next week.
Oh, okay. Right, but it's always better if we have more people who know how to do the different parts of it, right? Because like right now, if we needed to do something, some sort of change software, he's not here, right? Yeah, but yeah, we want to work on chemicals, that's fine. Okay, Ronnie, right? What do you want to work on?
Mechanical?
Okay. Drivetrain, shooter,
I
armor,
don't know.
all of it, any of it?
I don't know.
Yeah.
I don't know, but
Okay.
Mech, preferably chassis, drivetrain, and part of the shooter.
Mechanical, just anything they need, so any of it really.
programming.
Program, okay. Have you had any programming experience before?
Well, I did. I used to know a different programming language.
Which one?
Terrapin logo.
Never heard of that.
I learned it in elementary.
No,